before we get into some of the more serious definitions, we're going to revisit some examples that you know, and we are going to sort of try to give, at least in the case of rational numbers, a proper algebraic definition of what they are. So let me give you actually two descriptions of the rational numbers. And the first you're going to be a little bit familiar with. So usually we represent the rational numbers with this blackboard font Q, and we can think about it as a collection of fractions where a and b are integers and b is not 0. Now the problem is this is not true. The reason why this is not true is, as a definition, this doesn't incorporate, as it stands, it doesn't incorporate reducing fractions or having equivalent fractions. So what we actually do is we identify fractions if, well, when you cross multiply, you get the same thing. So technically it's this set, but we sort of mod out by an equivalence relation. Don't worry about what that means, but we have to do some identification process, because otherwise, if we don't identify these, then something like 4 over 2 and 2 over 1 would be considered different elements of Q. Because why? Well, they look different. They're not the same. They're with the exception of 2's, well, there's a 4 in one and there's no 4 in the other. So since sets care about just, is this element different than the other element, these would be different. So what we have to do is we have to take the set of all of these fraction-like objects, and then we have to identify a large portion of them with each other. In fact, we know from experience with fractions that every fraction you can represent in an infinite number of ways. So you have to identify, infinite number of elements with each other. So, anyways, what is the technical definition of Q? Well, it's this. Now, an alternative definition, which is sometimes seen in textbooks, is Q is the collection of all A ordered pairs AB, such that A and B are integers and B is not 0, and AB is related to CD if and only if AD is BC. Now the reason why this is often presented is because there's no algebraic definition for taking something and dividing by another. But it does make sense to take ordered pairs. This is kind of a subset, if you like, of Z cross Z, where we tap what's Z cross Z. It's ordered pairs of integers. Now it's not all of Z cross Z because we demand the denominator, the second coordinate, to be non-zero. But it's the same definition. Instead of viewing it as a fraction, we're viewing it as an ordered pair. But it's the same thing. It's pairs of integers, where the right integer is not 0, where the denominator is non-zero. And we have to regard them as being the same if and only if the cross product is the same, and it's the same definition. Great. Now the problem here is we haven't actually proved that this tilde is an equivalence relation. So in order for us to, for example, use the transitive property on fraction expressions or use the symmetric property, we actually have to prove them, right? It's not obvious. Well, it might be obvious to some, but not to me at least. So proposition, equivalence of fractions, we're going to use the first definition because that's what the book has, is an equivalence relation. Now later on we're going to do this fraction process with more general structures, and let me just be clear what the set is here first. And the proof is going to be exactly the same as this proof. So although this is going to appear kind of silly, it's actually not. Um, this proof ports over to whenever you're dealing with these fractional objects. And furthermore, there's something called taking the fraction field, and this is exactly what you do. So, anyways, this is not going to look very serious, but it actually is. It's a proof that you can copy and paste almost exactly. So, how do you prove something is an equivalence relation? We first show that it's reflexive. So A over B should be related to A over B. Okay, how do we show that A over B is related to A over B? Well, we need to show that the if and only if condition is satisfied. Namely, we have to show that the cross products are equal. So this says that AB is BA, but of course that's true because multiplication of integers is commutative. Commutativity of multiplication in Z. Great. So it's reflexive. We've just proven the reflexive property. Now we need to show symmetric. This is going to be more of a bullet style proof. So for symmetric, we need to suppose that A over B is related to C over D and show C over D is related to A over B. So let's write out our hypothesis. When we write that, we're saying that we know that AD is BC. What do we want to show? We want to show CB is DA. Oops, it's the wrong order here. Because that's what that's saying. That's what our conclusion is saying. But again, we have commutativity of multiplication. I'm just going to say comm of mult in Z. AD is BC is the same thing as saying DA is CB. And by the symmetric property of equality, this is saying CB is DA. So it's symmetric. Great. And then the last property is transitivity, which I'm not sure that I actually remember how to do, but we're going to try it out. So we're going to suppose AB is the same as C over D, and C over D is related to E over F. We need to show that A over B is related to E over F. So let's write out what our hypothesis is telling us. So we know that A over B is the same as C over D, and we know that C over D is the same as E over F. This is telling us then that the multiplication, cross multiplications are equal, and let's see, and CF is DE. Great. And let me also just point out, none of our denominators are 0. That's going to end up being important. Okay, what do we want to know? We want to show that A over B is E over F. So let's, I don't know, this one will be a circle. AF is BE. That's what we want to show. Okay, so I think what we can do to show this is, I think I want to take AD is BC, and we're going to multiply through, let's see, to leverage the F, I think we need to multiply through, we need to be able to leverage the F, we need to insert somehow here an F and an E. So I think I want to multiply by an FE, I think. So on the left-hand side, this is what we we're going to take and then we're going to multiply it by an FE to try to insert something there. So this is a true statement that we're producting with FE. So then what do we get here? I think what we're going to get is AFDE is, and then this guy I want to write as BECF. I think so.